Hello, thanks for the introduction and welcome to the talk on the application of a knowledge graph to enhance price analytics in the procurement domain. Before we look at the agenda, let me introduce myself. My name is Markus Nölke. I work for Siemens Energy now for more than 10 years. My office is located at the factory in Mülheim, close to Düsseldorf. As a cost value engineer, I act as a bridge between engineering, procurement, suppliers, with focus on improving our product cost position. For cost transparency and identification of cost out potential, I utilize extensively data analytics. In the presentation, I will explain the use case or motivation for the application of a knowledge graph in supply chain management and will present the implementation with details on used ontologies, patterns, and tools. The presentation is structured as follows. I will give a short overview about Siemens Energy and then explain what I mean by advanced price analytics, and will show you the related knowledge graph implementation. And I will close out with a short summary and next steps. But let us first start with the introduction of Siemens Energy. Siemens Energy is active in the energy market, mainly as an equipment supplier with a global footprint. More than 50% on the worldwide installed generation capacity is based on our technology. Although we have a fossil background, we are transforming to renewables, and our portfolio is already more than 50% carbon free. Along our core products, we offer solutions and services, mainly maintenance and repair. We have products in generation, transmission, and storage of energy. The portfolio ranges from conventional equipment like gas turbines to renewables like wind turbines through our daughter Gamesa, Siemens Gamesa, and to hydrogen generators. The use case currently focuses on conventional gas turbines. So let us have a look at the product structure and the related supply chain. Our product portfolio is quite large, including systems with subsystems or sub-subsystems. So here on the left, you can see there's a complete gas-fired power plant, which we sell, and what we also sell is just the gas turbine package, which is within this power plant. And the gas turbine package can be further broken down into the core engine, the gas turbine, the actual gas turbine, which we manufacture in-house, and also auxiliary elements like the air intake, which provides filtered air to the gas turbine. So this we buy complete as a system, but as mentioned, the gas turbine that is manufactured in-house. So here we need to further break down into components, which are quite numerous. So from machine parts to raw material, standard parts like bolts and nuts and so on. And so we buy all sorts of things from systems all the way down to raw material. And also Siemens Energy buys a lot, at about 10 billion euros annually is the purchase volume. Almost all components are engineered with lot size 1. They vary from project to project most often. Yeah, the specification are always need to always to be adapted. We have a global purchasing footprint with regional hubs and a global supply base, of course, following our projects and customers. And we have lastly, we're facing strong competition, and our cost base is heavily influenced, of course, by the external supply, and we have to buy at best price. And there we have finally our use case. We use data analytics to determine if we actually buy always throughout the entire organization at best price possible. And one example or one method here is the what we call the performance pricing. That means relating the price of a purchased item to its aspects and properties. So here is one example of a dashboard with an air intake portfolio where prices for air intakes are shown globally. For our entire gas turbine portfolio, from small gas turbines with low mass flow to large gas turbines with a large mass flow. And we have all the cost information mapped here in this chart over the mass flow. And we have one type of data is are estimated from our product tracking databases, for instance, from proposal calculation and so on. And the other prices are actually transaction prices from purchase orders, which are fixed. And these can also be shown here. And with this method, you can compare price over a wide range of application with varying parameters. The result might be a benchmark prices. So you can determine an average price line here, for instance, over the entire portfolio, or you can even determine a lowest price line, or you can investigate further outliers here and do further drill down. So also you can derive target cost here if you want. So if you design a new gas turbine and you just know the functional parameter mass flow, you can go in here and determine a price for this component, which is not actually designed at this point in time. So that is, as you can see, that is a very simple method with just one parameter, but in reality we have, of course, several parameters which are crucial for influencing the price, which we call cost driver, and they need to be evaluated in a multivariate regression. But also you can see that this easy statistical method also relies on the collection and integration of lots of data throughout the whole supply chain organization, but also integrating a lot of technical information. And that is the problem we try to solve with the knowledge graph. But there are some challenges, as probably in many organizations. We have unstructured data like pricing information comes PDF, technical documentation. We have Excel sheets, we have drawings, some information comes per email. Also, as shown, we have high complexity of products, so it's quite heterogeneous what we buy. We have also procurement and also engineering and manufacturing is distributed globally. We have that really resides also in different philosophies, legacy systems, and related vocabulary. And of course, we have data more organized in applications. And if data is pulled out of its relational databases, mostly the context is gone. So the general idea here is to use a good knowledge graph to integrate the data and defining a shared vocabulary across all the domains, procurement, engineering, technical vocabulary, but also service, for instance, and manufacturing. And there, the idea is to have a data integration platform based on a knowledge graph. And there we bring together all the transactional data, planning data, design data from various data silos, and we map them to the individual concepts, classes, and shared vocabulary, and we can evaluate it. And in that process, information becomes knowledge that can be formally processed by a machine. So here is one example. 500 is assigned a unit, which is defined in a core ontology, the QEDT. Then we have, okay, we say it's an inlet mass flow. It's a value for an inlet mass flow, which is defined in the domain ontology, but can also be defined by international standards. And then this inlet mass flow is mapped to technical asset, the air intake, which has also a corresponding semantic definition. It's a technical asset, which again is defined in the core ontology. And then, yeah, this data with a shared vocabulary, this map data can then be shared to applications through an API. And the apps can query content from the knowledge graph via Sparkle queries. And here we have also on the top our performance pricing dashboard, but also just simple query visualizations, traversing the graph, doing graph explorations is also possible. But let's look further at the ontology framework we are using here. So modeling scope, respectively technical assets, is done along with the ISO and the asset specification model from the READY project. So here the gas turbine, in this example, the gas turbine auxiliary system is modeled with a system engineering approach, starting with the main system and breaking it further down into sub-components all the way to the bottom here. So that generally is done related to aspects, to the aspects function, product, and location as per the ISO 81346. The product aspect is here omitted for the sake of simplicity. So function and location are here part of quite a different breakdown of hierarchies, and by mixing the two aspects, valuable contextual information is lost. And here also location can be referred to boundary conditions where you apply your technical assets. Along with the aspects, functional properties, which are modeled here, which is the power, for instance, requirement for the gas auxiliary system, and also the mass flow. We can also model location-related properties, which is wind speed, temperature, which is different indoor than compared to outdoor, and then an integrated object is created through connecting the respective objects in the hierarchies, and that is basically the specification for this air intake, and it's a functional object, and it integrates all the aspects, and all the requirements are then flowing down to this functional object. Then this object can be also related to offers being made for such an asset, or purchased orders being placed. And this gives the connection between the cost data and the technical parameters, which can then be utilized in the performance pricing method. But before we get to that, I show you how to model the properties. What are the typical property patterns here? Here we have the ISO 15926 14 pattern with a verification, which has a higher expressivity than modeling properties directly to the asset. So here we have the type of the property as an instance of a class, where the class is this is the nominal operating mass flow, which is defined by a GFOS standard. And it can also classify the functional object further into an oil and gas type of equipment. And then to this mass flow instance, we have the actual value connected, and also the unit, which is coming from QEDT or is mapped to the QEDT framework. For the purchase order or the quotation here, we have to map, for instance, a monetary value, which is a class from defined in the FIBO ontology, and there we have also the value, then the reification with the value connected, and also the currency connected, and the currency is defined also through the FIBO ontology, where you have all the currencies and all the country codes mapped and defined in the ontology. So yeah, and that brings us then to the integration and into our use case. And here's the example we looked at already. And here you can see how everything comes together. So we have here now our functional object, basically with the connected estimated as pricing, for instance, from a quotation. And we have the properties basically here from this asset specification model. So in this case, the mass flow, which are then mapped. So we have this connection here, and we have also the connection here to the purchase part, which is coming from a purchase order transaction for a different functional object. And that gives us the possibility to derive that dashboard in an automatic way for all sorts of technical assets which are defined in the knowledge graph, and all defined technical or properties or qualities we have in the knowledge graph, or which can be defined, and then we can do our analytics based on that. But to make that all work, we need reasoning. Here it's based on all or additional data log rules based on the RDF-OX implementation we have here in various areas. So one example here is the property allocation from the patronymies. So if here on top we have defined power requirement, it is then traveling down to the subcomponents basically. Also, the part of is also, it's a transitive property, so you have also that connection. But for instance, if the filtration is also part of the GT auxiliary system, that is then a separate property, so to not mix direct part relationship to indirect part relationships. Then we have the aggregation of cost. So if you have a calculation scheme where we have to add certain components and aggregate it into a higher scope, for instance, for mechanical equipment for a certain project, that is also done through reasoning. And we have the integration of the data with identifier matching. So here, ISO 81346 IDs can be used, or also legacy identifiers from the various databases to bring the data together. And then finally, we have constraint checking here with subclass requirements to check if certain technical assets where we have the requirements for certain technical values, if they are present, and also if they are in a certain range. And here, we need to rely also on closed word reasoning, which is also coming from the RDF-OX database technology. And that leads me to the architecture which is implemented. So this is the software architecture, starting from the data sources. So here we have a center query point via the Nodo. Through an OBDC connection, we can access, for instance, SAP data or other databases. We have connected Oracle database, Redshift data warehouse, and or a simple Excel sheets. And then, we can, via SQL, we can get the tabular data, and in the SQL lens, this data is then using the R2RML mapping files or mapping language, is then transferred into RDF, so-called NQuads, which contain also as a fourth dimension the provenance data that is put into the triple store, which contains all the provenance data and all historical data. And then, through either direct replication or special queries, we have connected our RDF-Ox reasoning engine, which is executing in memory, inferencing and reasoning based on data log rules or all ontologies. And that is the databases are queried through the Metafactory front end, which is a low-code tool to enable traversing through the graph and visualizing graph data within HTML pages. So the Sparkle queries can be directly incorporated in HTML pages. And also there are web connectors defined for a dashboard tool like Tableau, where you can directly then from Tableau query into through Metafactory query into the data in the graph database, which is not directly possible from Tableau. And also, you can through Metafactory you can realize certain class-based visualizations or just simple graph exploration schemes. And of course, that is then connected to a user management system. All right, that's all. So I would like to conclude the talk with a conclusion and also some next steps. So I think the knowledge graph is a good solution for applying performance pricing at scale. It really reduces the manual work we have to do right now to collect all the data, to clean to put it into a spreadsheet so we can analyze it. So with this approach, an automatic or semi-automatic performance pricing throughout all components we are buying is possible. But also what is I think clear is that the supply chain is a difficult domain to model because we are more interface discipline. So we rely on good data and the right data models from engineering, from the product lifecycle management. And also the models are quite heterogeneous, and that makes life difficult in the knowledge graph. And also, I think closed word reasoning is essential to get the reasoning we need to make connections and to do the constraint checking here. Possible next steps, I would say, from my perspective, is really adding equations. So once we have the statistical analytics in place and we have derived, for instance, a parametric formula for an air intake, I would like to put that into the graph and also do reasoning against that. So if let's say, identifying outliers based on that, and utilizing the numeric calculation also for further analytics. And also, of course, it would be very nice to link external data like a material index. So for instance, if you have so you can map, for instance, for all technical assets which use a certain carbon steel, you can map easily the price index and have direct information flowing into what are the price, what is the price increase for this particular raw material. Also very important for tracking price for tracking price movements in the market. Yeah, and lastly, I think also it's a good possibility to do data exchange with your business partners, with your suppliers, but also with your customers. So with suppliers, I could imagine that at the end that proposals are really exchanged through the knowledge graph, and we don't get PDFs which we have to then evaluate further, so and extract the valuable information, but so we can get already the semantic enriched information from a supplier. And also we have already projects with customers where they are asking for a certain data model, for instance in GFOS, which needs to be modeled then in a knowledge graph. Yeah, so that's concluding my talk, and yeah, I'm happy to answer additional questions. Thanks a lot.